Hello, friends. Welcome back. Or if this is your first time finding your way to these quiet nights with us, welcome. You arrived exactly when you were supposed to. Tonight we are going to travel somewhere no human has ever seen with their own eyes. Not to a distant galaxy, not to the edge of the solar system. We are going somewhere further than distance, somewhere before light itself existed. A universe so young, so dark, so completely silent, that even the stars had not yet learned what they were supposed to become. Before we drift in, if these slow journeys through science help you find some stillness at the end of your day, you might like to stay a little while. A gentle tap on the like button lets us know this kind of quiet is worth making more of. And if you would like the next story to find you, whenever the next night calls for it, a soft subscription and a ring of the little bell means it will know the way, not for noise, just so the next quiet journey can find you again. Now, let us begin. Picture the universe at 400 million years old. To us, that sounds ancient. But to a cosmos that is now 13.8 billion years old, 400 million years is barely a breath after waking. And at that age, the universe was doing something it had never done before and has never needed to do again. It was building its very first stars. But to understand the birth of the first star, we have to first understand what came before it. And what came before it was something that science has given a name so simple, so honest, that it almost sounds like a poem. Scientists call it the cosmic dark ages. Not dark in the way a cloudy night is dark. Not dark the way a room feels after the lights go out, but dark in the most complete sense that physics allows. A universe without a single photon of visible light traveling freely through space. No glow, no shimmer, no fire anywhere in all of existence. The Big Bang had happened. Energy had become matter. And that matter almost entirely hydrogen with a small fraction of helium and the faintest trace of lithium drifted outward in all directions into an expanding, cooling, thickening fog. The cosmos was not transparent yet. It was filled with a haze of neutral hydrogen gas so dense that, even if light had existed, it could not have traveled far before being absorbed. The universe was in the most literal sense opaque, closed to itself, unable to see what it was becoming. And here is something worth pausing on, because it is one of the most commonly misunderstood things about the early universe. Many people imagine the Big Bang as an explosion, a dramatic fiery burst that scattered stars and galaxies across space the way a shattered window scatters glass. But that is not what happened. There was no finished material flying outward. There were no stars, no galaxies, no planets. There was only raw energy cooling into simple atoms, and those atoms drifting in a darkness so complete it had no edges and no reference points. The universe did not explode into being. It expanded, slowly. And for a very long time, nothing much happened at all. This is the part of the story that most textbooks skip past quickly because it is on the surface uneventful. But there is something quietly extraordinary happening in that darkness. And it has everything to do with a force so subtle, so patient, that we rarely think of it as dramatic. Gravity. Not the gravity that pulls an apple from a tree, but gravity is a cosmic tendency, the universe's deep, unhurried preference for matter to be near other matter. In the very early universe, hydrogen gas was not spread with perfect uniformity. It could not be. Quantum fluctuations in the first fraction of a second after the Big Bang had left faint ripples regions that were ever so slightly denser than others. Not much. Perhaps 1 part in 100,000. But in a universe with no other forces in play, that tiny difference was enough. The denser regions attracted more gas. The slightly fuller clouds began to pull at the emptier spaces around them. Over millions of years, a whisper became a murmur became a current, and a current given enough time became a collapse. Scientists call these collapsing regions protogalactic clouds. Enormous structures of gas stretching across distances so vast that our entire Milky Way could have fit inside one of them comfortably. And within those clouds, smaller regions were pulling themselves inward as well. knots of density within knots of density, structure forming inside structure. The universe in the dark was slowly organizing itself. And here is where something happens that has no parallel in everyday experience. As a cloud of hydrogen gas collapses under its own gravity, it does not simply fall straight inward like a stone dropping to the floor. It begins to rotate. The reason for this goes back to those early quantum ripples. The gas does not fall symmetrically, and any slight angular momentum in the original cloud is preserved and amplified as the material pulls tighter. Like a figure skater drawing in their arms during a spin, the collapsing cloud rotates faster as it shrinks. It flattens. It heats. And at its center, a dense, hot core begins to form. This core has a name. It is called a protostar. And though it is not yet a star, not yet burning with the fire that defines a star, it is the universe's first attempt at making one. But the stars that formed from those earliest clouds were not like any star burning in the night sky today. They belong to a category that astronomers call population 3 stars. The naming, it must be said, is counterintuitive. Population 1, stars are the youngest generation. Population 2 are older, and population 3, theorized to be the very first, carries the highest number. The convention follows the order in which they were discovered, not the order in which they existed. It is one of science's small, harmless ironies. What made population 3 stars so different was what they lacked. Every star burning today, including our own sun, is made not just of hydrogen and helium, but of heavier elements: carbon, oxygen, silicon, iron. These elements did not exist in the early universe. They had to be forged inside stars and scattered into space when those stars died. The first stars had none of this material available to them. They formed from pure hydrogen and helium, and that absence changed everything about how they grew. Without heavier elements, there was less ability for the collapsing cloud to radiate away heat. Less heat loss meant higher internal pressure. Higher pressure meant the protostellar core could continue accumulating mass without fragmenting into many smaller stars. Theoretical models, and this is one of the most striking results in modern astrophysics, suggest these first stars may have grown to masses hundreds of times greater than our sun. Some simulations suggest that the most massive of them could have reached over 1,000 solar masses. They would have been almost unimaginably luminous, radiating with an intensity our sun cannot approach. And they would have been blue, burning hot and blue, and enormous, pouring ultraviolet radiation into the surrounding gas so intensely that the hydrogen fog began to ionize to break apart for the first time. This process is called cosmic reionization, and it marks the end of the cosmic dark ages. One by one, and then in clusters, the first stars switched on. The universe, which had been sealed in fog and darkness for hundreds of millions of years, began to clear. Light, for the first time, could travel freely through space. The cosmos opened its eyes. Have you ever wondered when you look up at the night sky whether any of those stars could possibly remember a time before other stars existed? Whether any light reaching your eyes tonight has been traveling long enough to carry some trace of the very beginning? It is not an idle question. Astronomers have asked it too. There is a star known as HD 140283, sitting approximately 200 light-years from Earth, close enough to observe in detail with modern instruments. For a period, early measurements suggested it might be older than the universe itself, which produced a reasonable amount of scientific alarm. Later, more precise measurements placed its age at around 13.7 to 13.8 billion years, balanced right at the very edge of what the current age of the universe permits. Astronomers nicknamed it the Methuselah star. It did not form from the population 3 generation, but it formed from gas enriched by them, gas that had been seeded with the first heavy elements scattered by those early stellar explosions. It carries written in its chemical composition the fingerprint of a generation of stars we have never directly seen, a memory of the beginning encoded in light that has been traveling long enough to reach us. And none of the population 3 stars themselves have ever been directly observed. Not one confirmed detection, Not a single image. This is not because scientists doubt they existed. Almost every model of cosmology requires them. It is because they were so massive and burned so fiercely that they exhausted their fuel in perhaps only a few million years. In cosmic terms, they were brilliant and brief. They lived fast and died in explosions of extraordinary violence, supernovae so energetic that they may have outshone entire young galaxies for brief periods. And in those deaths, they did something no star had ever done before. They released the heavier elements they had built in their cores, carbon, oxygen, the seeds of all future complexity, into the surrounding gas. They gave the universe the materials it needed to eventually make everything else, including billions of years later, the molecules of water and carbon and phosphorus that would assemble themselves into something that could wonder where it came from. This is what that long, dark silence was holding. Not emptiness, not meaninglessness, but the patient accumulation of all the conditions necessary for a universe to become complex enough to be curious about itself. For every atom in your body, a star had to be born and had to die. For those stars to be born, hydrogen had to collapse across hundreds of millions of years. For that collapse to begin a faint ripple in the density of a newborn universe, had to grow slowly into something gravity could hold on to. The chain reaches all the way back to the first second, and it reaches all the way forward to right now, to this breath, to this quiet moment in the dark. The universe spent the better part of 500 million years in silence before it made a single light. And then one by one, the lights came on. What we have talked about tonight is the very beginning, the darkness before the first stars, the slow pull of gravity that drew hydrogen out of the void, the brief and brilliant lives of stellar giants that burned so hot, they rewrote the chemistry of everything that followed. But the story of how a star is truly born, how a cloud moves from cold and dark to the first nuclear heartbeat at its core, is a journey that still lies ahead of us. And it begins as most extraordinary things do, in a quiet cloud of gas and dust, drifting in the dark, not yet knowing what it is about to become. There is a place in the night sky that the naked eye sees as nothing more than a faint smudge of light, barely visible below the 3 stars of Orion's belt. For centuries, people glanced at it and thought little of it. A blur, a smear, an imperfection in an otherwise crisp sky. But inside that smudge right now, as you read these words, stars are being born. Not metaphorically, not in some distant theoretical sense. Actual stars, condensing from gas and dust, heating toward the moment of their first nuclear breath. The Orion Nebula is the closest stellar nursery to Earth, and what it has taught us about how stars come into being has rewritten our understanding of the cosmos more than almost any other single object in the sky. We left the early universe in the glow of its first stars, those enormous brief population 3 giants that burned themselves out and scattered heavy elements into the surrounding gas. That was 13 billion years ago. But the process of star formation did not end with that first generation. It has continued quietly in the clouds and corridors of every galaxy ever since. And the place where it happens, the structure that cradles new stars into existence, is one of the most beautiful and strange objects that physics allows. It is called a nebula. And understanding what a nebula truly is requires letting go of almost everything the word suggests at first glance. Most people, when they hear the word nebula, think of the images, the sweeping colors, the pillars of rose and gold, the vast curtains of glowing gas that fill astronomy photographs, with something that looks honestly more like painting than reality. And it is worth addressing something here, because it matters for how we understand these objects. Those colors, the deep reds, the electric blues, the warm ambers of images like the Eagle Nebula or the Carina Nebula, are largely not what a human eye would see if it were somehow transported there. Most nebula photographs are taken using filters that capture specific wavelengths of light emitted by particular atoms, and those wavelengths are then mapped to visible colors for human display. Hydrogen alpha emission, deep in the red spectrum, is often shifted to pink or crimson. Oxygen 3 emission in the teal range becomes electric blue or green. The images are scientifically accurate representations of real emissions. They are not fabricated, but they are translations. The nebula itself, seen with unaided human eyes, would appear far dimmer, far more muted, perhaps a soft gray-green glow, perhaps almost nothing at all. And yet the reality of what a nebula is stripped of color enhancement is more astonishing than any image suggests. The Orion Nebula, catalogued as Messier 42 or M42, sits approximately 1,344 light-years from Earth. A single light-year is about 9.5 trillion kilometers. Multiply that by over 1,000, and you begin to approach the distance. The nebula itself spans roughly 40 light-years across a cloud of gas and dust, so vast that if you replaced our entire solar system with a grain of sand, the Orion Nebula would still be the size of a city block around it. And yet, in the context of the galaxy, it is a relatively modest cloud. There are nebulae in the Milky Way that stretch for hundreds of light-years. The Tarantula Nebula in the Large Magellanic Cloud spans nearly 1,000 light-years and is considered one of the most active star-forming regions in the known universe. If the Tarantula Nebula were located as close to Earth as the Orion Nebula, it would cast shadows at night. But size, impressive as it is not what makes a nebula extraordinary. What makes it extraordinary is what is inside it. A nebula is not simply empty space with a glow. It is a complex, structured environment made of several components, each playing a different role in the process of star formation. The bulk of the material is gas, primarily molecular hydrogen, meaning hydrogen atoms bonded in pairs designated H2. Unlike the atomic hydrogen of the early universe, molecular hydrogen forms in the cold, dense cores of clouds where temperatures can drop to as low as 10 Kelvin, 10 degrees above absolute zero. That is colder than the surface of Pluto, colder than almost anything in the natural solar system. In those frigid cores, chemistry happens slowly and strangely. Simple molecules form on the surfaces of dust grains. Water ice coats tiny particles. Carbon monoxide drifts through the dark in quantities that would be toxic beyond imagination if concentrated anywhere near a living thing. And it is the dust that is perhaps the most underappreciated ingredient in a stellar nursery. When astronomers talk about dust in space, they do not mean what settles on your bookshelf. Interstellar dust grains are tiny, typically between 1/100th and 1/10th of a micron in diameter, roughly the size of the particles in cigarette smoke. They are made of silicates, carbon compounds, sometimes iron, often coated in thin layers of ice. And they play several crucial roles in star formation. First, they block ultraviolet radiation from penetrating deep into the cloud, shielding the interior, and allowing molecules to survive that would otherwise be broken apart by high-energy light. Second, they provide surfaces on which molecules can form and stick. Third, and perhaps most importantly, dust grains radiate heat efficiently. When a region of a cloud begins to compress, dust helps carry thermal energy away, allowing the gas to remain cool enough to continue collapsing rather than heating up and pushing back outward. Without dust, star formation, as we know it, might be impossible. The dust is not a bystander, it is an architect. Now, here is a question worth sitting with for a moment. If gravity is constantly pulling this gas and dust inward, why is the cloud not already collapsed? Why does a nebula persist for millions of years without immediately forming stars? The answer is one of the more elegant balancing acts in all of astrophysics. A molecular cloud is not simply falling inward. It is held up temporarily, imperfectly, but genuinely by several competing forces. Thermal pressure pushes outward as the gas resists compression. Turbulence, vast, slow, swirling motions within the cloud, provides a kind of internal support. And in many molecular clouds, magnetic fields thread through the gas, providing a subtle resistance to collapse along certain directions. The cloud is not static. It is not peaceful. It is a dynamic, churning structure that is perpetually on the edge of collapsing, but perpetually also resisting. Star formation happens not when all resistance vanishes, but when local conditions tip slightly past the balance point, when a region inside the cloud becomes dense enough that its own gravity overcomes the pressure pushing outward. This tipping point has a name. It is called the Jeans instability, after the British physicist James Jeans, who worked out the mathematics of gravitational collapse in molecular clouds in the early 20th century. In 1902, Johns derived what is now called the Jeans mass, the critical mass above which a region of gas will collapse under its own gravity, and below which it will disperse. The Johns mass depends on temperature and density. Colder clouds collapse more easily because thermal pressure is lower. Denser regions collapse more readily because gravity is stronger at shorter distances. This is why the coldest, densest cores of molecular clouds are the places where stars are most actively forming. They are the regions most likely to cross the threshold that Jeans identified mathematically over a century ago. But Jeans worked out his equations under certain simplifying assumptions: a static uniform cloud without turbulence or magnetic fields. The real universe is considerably messier, and for decades after Jeans published his work, astronomers debated whether his equations could truly explain star formation in the wild complexity of actual nebulae. The answer, it turned out, is yes, but with important modifications. Real clouds need triggers. Something in most cases has to push a region of the cloud over the edge. One of the most important triggers for star formation is the shock wave from a nearby supernova. When a massive star ends its life in an explosion, it sends a ripple of compressed gas outward through the surrounding nebula. That shock wave sweeps up material, compresses regions that were hovering near the Jeans limit, and tips them into collapse. In this sense, dying stars give birth to new ones. A stellar death can trigger a stellar birth. The violence of an ending can be the catalyst for a beginning. This is not merely theoretical. There is strong evidence that our own sun may have been triggered into formation by a supernova explosion approximately 4.6 billion years ago. Certain isotopes found in meteorites, including aluminum-26, which is produced in supernovae and decays rapidly, suggest that our young solar system was contaminated with freshly produced stellar material very shortly before the sun formed. The timing implies a nearby explosion. A shock wave that compressed the cloud that would eventually become our solar system pushed it past the tipping point and set in motion the chain of events that would eventually, billions of years later, include you. It is one of the more quietly staggering things that planetary science has uncovered. We may owe our existence to a star that died before our sun was born. Other triggers exist as well. The spiral arms of galaxies, great sweeping density waves that rotate through the disk of a galaxy, like a slow, enormous compression, are powerful concentrators of molecular gas. As clouds drift into the high-pressure region of a spiral arm, they are squeezed. Density rises. Temperatures in cores drop. The Jeans threshold is crossed. This is why, when we look at nearby spiral galaxies like Andromeda or the Triangulum galaxy, we see bright clusters of young blue stars tracing the spiral arms. Those are the regions where compression has been most recently triggering stellar birth. Within the Orion Nebula, specifically, the star formation we observe today is thought to have been triggered partly by the Orion OB1 association, a group of massive hot stars that formed a few million years ago, and whose ultraviolet radiation and winds have been compressing the surrounding gas, carving out the structures we see. The Trapezium Cluster, a tight group of 4 exceptionally bright young stars, visible near the center of the Orion Nebula, even with a small telescope, is the primary source of ionizing radiation, lighting up the nebula around them. They are new. Cosmically speaking, they are newborns. And the light they produce is illuminating the very cloud from which they emerged. There is a structure within that nebula, however, that has become perhaps the most iconic image in the history of stellar nursery science. And it was captured not by the Hubble Space Telescope, which is often credited for it, but by a dedicated campaign of observations that included multiple instruments. It is called the Pillars of Creation. The pillars of creation are columns of dense gas and dust inside the Eagle Nebula, approximately 6,500 light-years away in the constellation Serpens. They were first photographed in stunning detail by Hubble in 1995, and the image became one of the most reproduced astronomical photographs in history. The pillars stretch between 1 and 4 light-years in height. At their tips, dense knots of gas called EGCGs, evaporating gaseous globules, are being sculpted by radiation from nearby hot stars. Inside some of those EGGs, protostars may be forming. The pillars are in effect a snapshot of star formation, being simultaneously triggered and destroyed, compressed at their dense tips by radiation pressure, while that same radiation slowly ablates the outer layers of the column. It is worth noting something that often surprises people when they learn it. The pillars of creation that we see in photographs may no longer exist. Light travels at a finite speed, and the Eagle Nebula is over 6,000 light-years away. The light we see left those pillars 6,000 years ago. Astronomers using infrared data from the Spitzer Space Telescope have found evidence suggesting that a shock wave from a nearby supernova may have reached the pillars roughly 6,000 years ago. That shock wave, traveling at a fraction of the speed of light, could have already disrupted or destroyed the pillars entirely. What we see in those photographs may be a ghost, a preserved image of something that no longer exists, preserved for us by the finite speed of light. We are seeing the past and the present. The pillars may already be gone. This is a characteristic of astronomy that takes time to fully absorb. We never see the universe as it is. We see it as it was always looking back in time, the distance in space translating directly into distance in time. The farther we look, the older the image. And at the scale of thousands of light years, we are not looking back by years or centuries, but by millennia. Every nebula we observe is a historical document, a photograph from the deep past arriving on our detectors as a message from a time before human civilization existed. Have you ever held a photograph so old that the people in it are gone and felt the strange weight of time in your hands? Looking at the pillars of creation carries something of the same feeling, but stretched across 6,000 years instead of a human lifetime. The molecular clouds and nebulae we have been exploring, these cold, dark, turbulent nurseries, are the stage on which the next act of our story takes place. We have seen how they form what holds them together, what pushes them toward collapse, and what extraordinary triggers can tip a stable cloud into the beginning of a star. We have walked through the Orion Nebula, stood at the base of the pillars of creation, and understood perhaps for the first time that the colors in those beloved images are translations of invisible light into something our eyes can receive. But inside the densest cores of these clouds, something has already begun that we have not yet followed all the way through. Gravity has won. The collapse has started, and in the cold, dark heart of a molecular cloud, something is falling inward right now, gathering mass, building heat, spinning slowly toward the moment when it crosses a threshold that no cloud can cross and come back from. The protostar is waking up. There is a force acting on you right now that you cannot see, cannot hear, and almost never think about. It is holding you to the surface of this planet. It is keeping the moon in its slow orbit overhead. It is bending the path of light itself as it travels across the universe. And 4.5 billion years ago, it reached into a cold, dark cloud of gas and dust, and it pulled, slowly, patiently, without urgency, and from that pull, a star was born. The same force that keeps your feet on the ground is the same force that built the sun. Gravity does not announce itself. It simply works. And the story of how it turns nothing into everything is one of the most quietly astonishing things science has ever worked out. We left our molecular cloud at a moment of decision, a dense core tipping past the gene's threshold, beginning to fall inward. The triggers were there, a shock wave perhaps from a dying star nearby, or the slow compression of a spiral arm, or simply the patient accumulation of enough mass in one place that the balance finally broke. Now, the collapse has begun. And to understand what happens next, we need to understand gravity not as a simple downward pull, but as a sculptor, one of the most patient and precise sculptors the universe has ever produced. Isaac Newton gave us the mathematical language for gravity in 1687, in a work that is perhaps the most consequential single publication in the history of science. The Principia Mathematica laid out in elegant geometric form the law that every mass attracts every other mass with a force proportional to their masses and inversely proportional to the square of the distance between them. It sounds clean and simple, and for many purposes it is, but Newton himself was deeply uncomfortable with one aspect of his own theory, and he said so in letters to his contemporaries. The theory described how gravity worked with extraordinary precision. It could not explain why. It could not explain what gravity actually was, what the mechanism was by which the sun, 93 million miles away, could reach across empty space and hold the Earth in its orbit without anything physically connecting them. Newton called it action at a distance, and he found it troubling. He wrote that gravity should be innate, inherent, and essential to matter, so that one body may act upon another at a distance through a vacuum without the mediation of anything else by and through which their action and force may be conveyed from one to another, is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. He described the mechanism perfectly. He admitted he had no idea what it was. That question, what gravity actually is, would not receive a truly satisfying answer for another 228 years. And when the answer came, it came from a 26-year-old patent clerk in Bern, Switzerland, who was thinking about what it would feel like to fall. Albert Einstein published his general theory of relativity in 1915, and it reframed gravity entirely. Gravity in Einstein's description is not a force at all in the traditional sense. It is a curvature of space-time, the four-dimensional fabric of the universe caused by the presence of mass and energy. Matter tells space-time how to curve. Space-time tells matter how to move. What we experience as the pull of gravity is simply the natural path that objects follow through curved space-time. The Earth does not fall toward the sun because some invisible rope is pulling it. It follows a curved path through the space-time that the sun's mass has bent, and that curved path is what we call an orbit. This distinction matters for understanding stellar formation in a way that goes beyond philosophy. In Newtonian physics, gravity seems like a simple constant pull. In Einsteinian physics, we understand that gravity is a geometry, and the geometry changes depending on how mass is distributed and moving. A collapsing cloud of gas does not simply fall inward like water down a drain. It responds to a changing geometry. And the geometry of that collapsing cloud is determined not just by its total mass, but by how that mass is distributed, how fast it is moving, how it is rotating, and how the surrounding environment is shaped. Now here is where something genuinely beautiful enters the story, something that casual discussions of star formation often skip entirely. As a molecular cloud core collapses under gravity, it does not fall symmetrically. Real clouds are not perfect spheres. They are lumpy, asymmetrical, threaded with magnetic fields shot through with turbulence. And even if they were perfectly uniform to begin with, which they are not, any tiny asymmetry in the initial conditions is amplified enormously as the collapse proceeds. The cloud does not simply shrink. It develops structure. It fragments. It spins. The spinning is worth dwelling on for a moment because it is one of those facts that seems almost magical until you understand the physics behind it, and then seems even more magical. As the cloud collapses, any net rotation, it had even an imperceptibly slow rotation, is conserved and amplified. This is the same principle that makes a spinning figure skater rotate faster when she pulls her arms inward. Angular momentum, the product of rotational speed and the distribution of mass, is conserved in the absence of external torques. As mass falls inward and the cloud shrinks, the distribution of mass becomes more concentrated toward the center. To conserve angular momentum, the rotation rate must increase. A cloud that was rotating so slowly its motion would be invisible to any instrument we possess begins as it shrinks to spin faster and faster. The outer regions falling inward are deflected by this rotation into orbits around the central core. The collapse in the plane of rotation is slowed. The collapse along the rotation axis continues. The result is a flattened rotating disk of gas and dust around a central concentration of mass. This disk, called a protostellar disk, or in later stages a protoplanetary disk, is not merely an interesting byproduct. It is the structure from which planets, moons, asteroids, and comets will eventually form. The same physics that builds a star also lays the foundations for everything that orbits it. Our own solar system tells this story in its geometry. All 8 planets orbit the Sun in roughly the same plane. They all orbit in the same direction. The Sun itself rotates in the same direction. This is not a coincidence. It is the preserved signature of the rotation of the molecular cloud core that collapsed to form the solar system 4.6 billion years ago. Every time you look at a diagram of the solar system, that flat disk of orbiting worlds around a central star, you are looking at the fossil of a gravitational collapse. The shape of the solar system is the shape of the physics. But let us return to the core of the collapsing cloud. As material falls inward, several things happen simultaneously. The density of the central region increases. As density increases, the region becomes less transparent to radiation. Less radiation can escape. The temperature begins to rise. And as temperature rises, thermal pressure begins to push back against the collapse. This creates the first of several distinct phases in the life of a forming star, a phase called the first hydrostatic core, which is not a star by any definition, but is no longer simply a cloud. It is something in between, a warm, slowly collapsing ball of gas, approximately 5 times the radius of the Sun, rotating, held temporarily in a quasi-equilibrium between gravity pulling in and thermal pressure pushing out, radiating in the infrared. It is invisible in ordinary light. It glows only in wavelengths our eyes cannot detect. For much of the 20th century, this phase of star formation was purely theoretical. Astronomers could model it mathematically, but they could not observe it directly, because the protostellar core is deeply embedded in a thick cocoon of gas and dust that blocks all optical light. Even infrared light is partially absorbed. Only the longest wavelengths, sub-millimeter and millimeter radiation, penetrate deeply enough to reveal what is happening inside. And so, for decades, the first hydrostatic core remained a prediction without a confirmed observation. In 2010, a team of astronomers using the sub-millimeter array in Hawaii announced a candidate, a deeply embedded source in the Perseus molecular cloud complex, designated L1448IRS3b, that had properties consistent with the theoretical first hydrostatic core. The detection was tentative, the evidence was debated, but it was the first glimpse of what had previously existed only in equations. In subsequent years, more candidates were identified. The James Webb Space Telescope, with its extraordinary infrared sensitivity, has provided new windows into these deeply hidden objects, revealing structures and temperature gradients that match theoretical predictions with increasing precision. The history of gravity as a scientific concept is in many ways a history of increasing humility. Newton gave us the mathematics and admitted he did not understand the mechanism. Einstein gave us the mechanism space-time curvature, and the theory was so successful that it seemed for a while complete. But general relativity and quantum mechanics, the two great pillars of 20th century physics, are mathematically incompatible at the extremes. At the scale of black holes, at the scale of the Big Bang itself, the two theories give contradictory answers, and no one yet knows how to reconcile them. Gravity, the oldest and most familiar force, remains the least understood at its deepest level. And yet, in its patient large-scale operation, in the collapse of molecular cloud cores, in the flattening of protostellar disks, in the gentle spiral infall of gas toward a forming star, gravity reveals itself to be not just a force, but a storyteller. It takes disordered, turbulent, irregularly distributed matter and imposes structure. It takes randomness and makes patterns. It takes a cold, featureless cloud and sculpts it over hundreds of thousands of years into something with a center, a disk, a rotation, a direction. Something that has already, in some sense, decided what it is going to become. There is a question worth asking here, and it is one that scientists genuinely wrestle with. If we could stand somewhere outside our solar system and watch the cloud that became the sun begin its collapse 4.6 billion years ago, would we recognize from the very beginning what it was going to become? Would the mass and rotation and chemical composition already carry within them the signature of a yellow dwarf star, of 8 planets, of a small, wet third planet with a thin atmosphere, and something on its surface that would eventually look up and ask questions? The physicists who work on star formation say carefully that the outcome is not strictly deterministic in every detail. Turbulence is chaotic. Small differences in initial conditions can produce meaningfully different results. The exact arrangement of the planets in our solar system may have been sensitive to initial conditions in ways we can never reconstruct. But the broad outcome, a star of roughly the sun's mass, was probably written into the mass of the original cloud core from very early on. The gene's mass at the moment of collapse was already pointing toward what would emerge. Gravity in that sense is not just patient. It is in its quiet way purposeful. This is of course a poetic reading of pure physics. Gravity has no purpose in any conscious sense. It follows equations. It obeys geometry. But when those equations and that geometry conspire over hundreds of millions of years to take hydrogen scattered through the void and fold it into a star that warms a planet, that generates life, that generates music and mathematics, and the ability to wonder where it all came from, it becomes very difficult not to feel that something extraordinary has been at work. Newton sat under a tree or so, the legend goes, though historians note the story was probably embellished by Voltaire and watched an apple fall. He asked why, and in asking why, he set in motion a chain of inquiry that would eventually reach across centuries to Einstein, and from Einstein to the quantum theorists who still cannot fully reconcile what gravity is at its smallest scales. Science is, among other things, the long, patient asking of questions that gravity first suggested on an autumn afternoon in 1666. Have you ever felt the pull of something you could not explain, a direction things seemed to naturally move a weight at the center of something, that everything else organized around gravity does that to gas? It does it slowly and visibly without drama, and the result eventually is a star. The collapse we have been following, the slow infall, the flattening disk, the warming core has now reached a point where gravity has done its primary work. The protostellar core is sitting at the center of a rotating disk, gathering mass from the surrounding envelope, growing warmer with every passing 1,000 years. The first hydrostatic core has become something more substantial, something that, in the right infrared wavelengths, genuinely glows. What is formed sitting hidden inside its cocoon of dust and gas, wrapped in silence and heat, is a protostar. Not yet a star in any full sense, not yet burning, not yet in balance, but already something, already a beginning. And the story of what the protostar is, what it does, what it struggles against, and what it cannot yet achieve. That story is one of the most intimate and surprising in all of stellar science. Somewhere in the Perseus molecular cloud, about 1,000 light years from where you are sitting right now, there is an object that has no name most people would recognize. It does not appear in any constellation. It cannot be seen with the naked eye, or with an ordinary telescope, or even with a powerful optical instrument pointed directly at it. It is wrapped so completely in a cocoon of gas and dust that visible light cannot escape from it at all. And yet right now at this very moment, it is one of the most dynamic, energetic, and consequential things happening in our region of the galaxy. It is a protostar in the middle of its formation. It is a star that has not yet learned what it is. And the story of what it is going through, the pressure, the heat, The violent outflows, the slow and agonizing approach toward a threshold it may or may not ever cross, is one of the most dramatic stories that happens in complete silence and total darkness, completely invisible to human eyes. We arrived here following gravity's patient work, the collapse of a molecular cloud core, the flattening into a rotating disk, the first hydrostatic core warming at the center of a shrinking envelope. That work is not finished. It has only just reached its most interesting chapter. Because what gravity has built so far is not yet a star. It is a protostar. And the difference between those two words contains an entire world of physics. Let us be precise about what a protostar actually is, because this is a term that is frequently misused even in popular science writing. A protostar is not simply a young star. It is a specific phase in stellar evolution, a phase defined not by age but by its energy source. A true star, in the technical definition used by astrophysicists, is an object that generates energy primarily through nuclear fusion in its core. A protostar does not yet do this. Its energy comes from a different source entirely: gravitational contraction. As material falls onto the protostellar core, and the core itself slowly shrinks under its own weight, gravitational potential energy is converted to thermal energy. The protostar shines not because it is burning hydrogen, but because it is falling. It is luminous because it is collapsing. And this distinction between gravitational energy and nuclear energy is the boundary between a protostar and a star. The crossing of that boundary is one of the most significant events that can happen in the universe. The physicist who first worked this out in a satisfying mathematical framework was not a 20th century astrophysicist working with computers and radio telescopes. He was a 19th century German physicist named Hermann von Helmholtz, working in the 1850s, followed closely by the British physicist William Thomson, later known as Lord Kelvin, who refined the calculations in the 1860s. Together, they developed what is now called the Kelvin-Helmholtz mechanism, the process by which a self-gravitating body of gas radiates energy derived from its own gravitational contraction. At the time, it was proposed not to explain star formation, but to explain the sun itself. The question being asked in the mid-19th century was a profound and troubling one. What is the sun burning, and how long can it last? Before nuclear physics was understood, the Kelvin-Helmholtz mechanism seemed like the most plausible answer. If the sun were slowly contracting, converting gravitational energy to heat and light, how long could it sustain its current luminosity? Kelvin and Helmholtz calculated the answer: approximately 20 to 40 million years. This was an enormous span of time by human standards, but it was deeply problematic for another emerging science. Charles Darwin had published On the Origin of Species in 1859, and geologists were increasingly certain, from the evidence of rock strata and sediment accumulation, that the Earth was hundreds of millions of years old, perhaps far older. If the sun could only have been shining for 20 million years, then Darwin's slow, gradual evolution could not have had time to produce the diversity of life on Earth. The physicists and the biologists were in direct contradiction. And for several decades, this was a genuine crisis in science, with Lord Kelvin himself repeatedly and publicly attacking the geologists and biologists for their seemingly impossible timescales. The resolution came only in the early 20th century, when radioactivity was discovered and nuclear physics revealed a new and vastly more powerful energy source. The sun is not powered by gravitational contraction. It is powered by nuclear fusion. And with fusion as its energy source, the sun's lifespan extends not to tens of millions of years, but to tens of billions. The geologists and biologists were right. Kelvin was wrong about the sun, but he was not wrong about the mechanism, because the Kelvin-Helmholtz mechanism is exactly what powers a protostar. In the earliest phase of stellar formation, before nuclear fusion ignites, gravitational contraction is the energy source. Kelvin described the wrong phase of the sun's life. He described the right physics for the phase before it. This is one of the more elegant reversals in the history of science. A theory that was believed to explain the present sun was eventually shown to describe the sun's infancy instead. The answer was not wrong, it was simply early. Now, what does a protostar actually look like from the outside? The answer is, it depends entirely on the wavelength you use to observe it. In optical light, the light your eyes detect the light of ordinary photographs, a protostar is invisible. Its host cloud absorbs and scatters every photon of optical light before it can escape. In near-infrared wavelengths, a faint glow might be detectable, scattered by dust particles in the outer envelope. In mid-infrared, the warm dust of the surrounding envelope radiates brightly. In far-infrared and submillimeter wavelengths, the cold outer layers of the cloud emit radiation that can be detected and mapped. And in radio wavelengths, molecular line emission from molecules like carbon monoxide traces the velocity structure of the infalling and outflowing gas with extraordinary detail. Astronomers classify young stellar objects, the broad category that includes protostars, using a system based on their spectral energy distribution, meaning the way their brightness varies across wavelengths. Class 0 objects are the youngest protostars so deeply embedded that they emit almost entirely in the far infrared and submillimeter, with no detectable optical or near-infrared light at all. Class 1 objects have developed enough that they show a near-infrared excess. The disk and inner envelope are warm enough to radiate at shorter wavelengths. Class 2 objects, sometimes called T-Tauri stars, have largely cleared their surrounding envelope and are optically visible, still surrounded by a disk, but no longer embedded. Class 3 objects have largely dissipated their disks and are approaching the main sequence. The protostar phase spans classes 0 and 1, and in the most actively observed star-forming regions, all of these classes are present simultaneously, different objects at different stages of the same long journey. The Perseus molecular cloud complex, which was mentioned as home to some of the best-studied young stellar objects in the sky, contains several Class 0 protostars that have become benchmarks for understanding the earliest phases of stellar evolution. Among them is a system called NGC 1333 IRAS4, a binary protostellar system, 2. Protostars forming together from the same collapsing core embedded so deeply in its cloud that it was not detected at all until infrared and radio observations became sensitive enough to penetrate the dust. Observations of this system, with the Atacama Large Millimeter Array known as ALMA, have revealed the detailed structure of infalling gas rotating disks and outflowing jets with a resolution that just 2 decades ago would have been considered impossible. We are living in a golden age of protostellar observation, and most of the public does not know it. The outflows are worth particular attention because they represent something that surprises almost everyone who encounters star formation for the first time. A protostar, despite being in the process of accumulating mass from its surroundings, is simultaneously expelling material back outward along its rotation axis. These outflows, called bipolar outflows or protostellar jets, can extend for light years in both directions, launching material at speeds of hundreds of kilometers per second into the surrounding cloud. The jets are collimated, focused into narrow beams by the magnetic field of the protostellar disk, which acts like a nozzle channeling gas that has been lifted off the disk surface by magnetic forces and accelerating it outward. When these jets slam into the surrounding cloud material, they create bright shock fronts called Herbig-Haro objects, which appear as glowing knots and arcs of ionized gas in deep images of star-forming regions. The Herbig-Haro objects were first cataloged by the American astronomer George Herbig and the Mexican astronomer Guillermo Haro, working independently in the early 1950s. And both published their findings in 1952. Herbig was observing in the Orion Nebula and noticed small nebulous patches that did not fit the appearance of any known object type. Haro, working in Mexico City, observed similar objects and published his own catalog. When the astronomical community recognized that they were seeing the same phenomenon, the objects were named after both astronomers, a relatively rare instance in the history of astronomy, of a discovery being shared equally between researchers working completely independently on opposite sides of the hemisphere. We now know that Herbig-Haro objects are the visible traces of protostellar jets, and they have become one of the primary tools for identifying and studying actively accreting protostars. When you see a Herbig-Haro object, you know that somewhere along the axis, it points towards somewhere buried deep in the cloud. A protostar is actively gathering mass and launching jets. The object is a signpost, a trace left in the cloud by a forming star that cannot itself be seen. There is a common misconception about protostars that deserves to be addressed directly because it appears even in some introductory astronomy textbooks. The misconception is that a protostar is simply a very young star, essentially the same object as a star just earlier in time. This framing misses something fundamental. A protostar is qualitatively different from a star, not just quantitatively younger. It is larger than the star. It will become far larger in most cases. A solar mass protostar in the class 0 phase may have a radius several times larger than the eventual main sequence star. It is cooler at its surface despite its large luminosity because that luminosity is spread across such an enormous area. It pulsates. It is magnetically active in ways a stable main sequence star is not. And it is still gaining mass. It has not yet reached its final mass and will not until the surrounding envelope has been accreted or dispersed. In other words, a protostar is not a small version of its future self. It is a different kind of object altogether in a transitional phase between a cold cloud and a hot star occupying a middle territory that has its own physics, its own characteristic timescales, and its own distinctive signatures in the sky. The duration of the protostellar phase varies with mass. For a solar mass star, the combined class 0 and class 1 protostellar phase lasts roughly 500,000 years, a geological eye blink by cosmic standards, but still 500,000 years during which gravity is building something extraordinary. For more massive stars, the collapse is faster, and the protostellar phase shorter, sometimes only a few thousand years. For lower mass stars, which will eventually become red dwarfs, the protostellar phase can extend considerably longer. Time, like almost everything else in stellar formation, scales with mass. And what does it feel like if we allow ourselves for a moment the poetic license of imagining an interior perspective to be inside a protostar? The core is hot by everyday standards, several thousand Kelvin, but cool by the standards of what it will eventually need to become. The pressure is building slowly but relentlessly, as in falling material adds its weight from above. The rotation is a presence everywhere, the disk turning steadily in the equatorial plane, the jets launching outward from the poles, the magnetic field threading through everything and connecting the core to the disk to the outflows in a tangled dynamic web that simulations still struggle to fully capture. It is not peaceful, it is not silent, but the noise of it, the shock fronts, the magnetic reconnection events, the turbulent infall happens on time scales and spatial scales that would make it appear from the outside utterly serene. A slowly brightening glow in an infrared image, a slight increase in millimeter flux from one observation to the next, years apart. Have you ever watched something change so slowly that you could not perceive the change directly, only by comparing two photographs taken years apart? The growth of a tree over a decade, the gradual shifting of a river channel over centuries. The protostar changes at that pace or slower, and yet the physics driving it is anything but gentle. There is one final thing about the protostellar phase that carries a kind of weight worth sitting with quietly. Everything that will eventually exist in the solar system that forms from this protostar, every planet, every moon, every comet, every grain of dust in every asteroid belt, is right now still part of the protostellar envelope. The atoms that will one day form the iron core of a rocky planet are currently falling inward through the rotating disk. The molecules that will one day become part of an ocean are drifting in the gas envelope. Nothing has been decided yet. The material is still in motion, still sorting itself by density and temperature, and volatility still obeying the laws of physics moment by moment, without any knowledge of what it is becoming. And yet, the outcome, a star surrounded by a system of worlds, is already in some sense written into the initial conditions of the collapse. The protostar sits at the center of all of this gathering mass, launching jets swarming slowly toward the most important threshold in its existence. The core temperature is rising. The pressure is rising. Hundreds of thousands of years of gravitational contraction have been building toward a single moment, a moment that when it arrives will not look dramatic. From the outside, will not produce a flash or an explosion visible across the galaxy, but will nonetheless be one of the most profound transitions that matter can undergo. The hydrogen at the core is approaching the temperature at which it can no longer simply be heated. It must react. The first nuclear heartbeat is almost here. In 1920, a British astrophysicist stood up at a scientific meeting and made a claim so far ahead of its time that most of his colleagues thought he had simply lost his grip on reality. He suggested that the sun, that vast ancient blazing object that had been worshipped as a god and studied as a mystery for all of human history, was powered by the fusion of hydrogen atoms into helium, that the energy of the sun came not from burning, not from contraction, not from any chemical or mechanical process, but from the conversion of mass into energy inside an atomic nucleus. His name was Arthur Eddington. He was 37 years old, and the physics he needed to fully prove his idea did not yet exist. The other scientists in that room were polite. Some were respectful. Most were unconvinced. It would take another 38 years and the combined work of dozens of physicists across 3 continents, including several who would go on to win Nobel Prizes before the precise chain of nuclear reactions powering the sun was worked out in complete detail. Eddington was right. He was simply right too early. And the story of how that first nuclear fire lights inside a forming star is the story of one of the most consequential transitions in the universe. We have been following our protostar through its long, patient accumulation, the gravitational collapse, the formation of the disk, the launching of jets, the slow warming of the core as infalling material adds its weight from above. The core has been heating for hundreds of thousands of years. The pressure has been building. And now, we arrive at the threshold, the moment when temperature and pressure at the center of the protostellar core reach values that the universe has been building toward since the first hydrogen atoms formed in the minutes after the Big Bang. We arrive at the ignition of nuclear fusion. And to understand why this moment is so extraordinary, we need to understand something that seems at first like a paradox. Nuclear fusion should be impossible. 2 hydrogen nuclei are both positively charged. Like charges repel. The electrostatic repulsion between 2 protons, the Coulomb barrier as physicists call it, is an enormous obstacle. At the temperatures and pressures inside a forming stellar core, the thermal energy of the protons is simply not high enough to overcome this barrier through classical physics. If you calculate the temperature needed for protons to collide with enough energy to classically surmount the Coulomb barrier and fuse, you arrive at a number approximately 1,000 times higher than the temperature at the center of the sun. The sun should not be able to fuse hydrogen, and yet it does, every second, at a rate that has sustained it for 4.5 billion years and will sustain it for another 5 billion more. The resolution to this paradox comes from quantum mechanics, specifically from a phenomenon called quantum tunneling. In the quantum world, particles do not have precisely defined positions and momenta in the way that classical objects do. They exist as probability distributions spread across a range of possible locations and states. And because of this spread, there is a finite probability that a proton approaching another proton can appear as if by quantum sleight of hand on the other side of the Coulomb barrier without having enough classical energy to cross it. It tunnels through, not over, through. This is not a metaphor or a simplification. It is a mathematical reality confirmed by both theory and experiment that quantum particles can traverse barriers that classical particles cannot. And at the temperatures and densities inside a stellar core, where protons are colliding billions of times per second, even a very small probability of tunneling per collision translates into an enormous rate of fusion overall. George Gamow, the brilliant and eccentric Russian-American physicist, worked out the mathematics of quantum tunneling through the Coulomb barrier in 1928. He was 24 years old. His calculation provided the theoretical foundation that made it possible a decade later for Hans Bethe and Carl Friedrich von Weizsäcker to independently work out the precise nuclear reaction chains responsible for energy production in stars. Bethe published his comprehensive analysis in 1939, and it earned him the Nobel Prize in Physics in 1967, a recognition that arrived nearly 3 decades after the original work, which is itself a lesson in how slowly scientific revolutions are sometimes acknowledged. The primary fusion reaction in a star like the Sun is called the proton-proton chain. It begins with 2 protons fusing to form a deuterium nucleus, a nucleus containing 1 proton and 1 neutron, releasing a positron and a neutrino in the process. The deuterium then fuses with another proton to form helium-3, releasing a gamma ray. 2 helium-3 nuclei then collide to produce helium-4 ordinary helium and release 2 protons back into the mix. The net result of this entire chain is that 4 hydrogen nuclei have been converted into 1 helium-4 nucleus, 2 positrons, 2 neutrinos, and energy. The energy released corresponds to the small difference in mass between the 4 input protons and the single output helium nucleus. That mass difference, about 0.7% of the total input mass, is converted directly to energy. According to Einstein's equation, E equals mc squared. 0.7% sounds negligibly small, but c squared the speed of light multiplied by itself is an almost incomprehensibly large number. Multiplying even a tiny mass by that number produces an enormous quantity of energy. And in a stellar core where this reaction is occurring continuously across a volume larger than the entire Earth, the total energy output is staggering. Now, the question that connects this nuclear physics to the story we have been following is what exactly happens at the moment when fusion first ignites in a protostellar core. Is there a flash, an explosion, a sudden dramatic brightening visible across the nebula? The answer, and this is one of the things that makes stellar physics genuinely surprising, is that the ignition of hydrogen fusion in a protostar is not an event that most outside observers would notice at all. It does not produce a burst. It does not create a detectable explosion. The reason for this lies in the remarkable self-regulating nature of the fusion process inside a star. When fusion begins and starts generating energy, that energy creates additional thermal pressure in the core. This pressure pushes back against the gravitational contraction that has been heating the core. The contraction slows. The temperature stabilizes. The rate of fusion adjusts itself to exactly the level needed to maintain the core at the temperature where the outward pressure of fusion energy precisely balances the inward pull of gravity. The star finds an equilibrium, and it does this quietly, smoothly, without drama, the way a thermostat brings a room to the right temperature, and then simply holds it there. This equilibrium state where fusion energy exactly balances gravitational pressure is called the main sequence. And the transition from protostar to main sequence star, from a body powered by gravitational contraction to a body powered by nuclear fusion, is called the zero-age main sequence, or ZAMS. The moment a forming star reaches this point, its long protostellar journey is over. It has become a star. Not because anything explodes, not because anything flashes, but because an internal balance has been achieved quietly in the dark of its own core. Arthur Eddington, in that 1920 lecture, where he proposed hydrogen fusion as the sun's energy source, said something that has since become one of the most quoted passages in the history of astrophysics. He observed that if stars are indeed fusing hydrogen into helium, then the sun contains enough fuel to shine for billions of years, and this alone was enough to resolve the conflict between the physicists who calculated a young sun and the geologists and biologists who required an ancient Earth. He then went further and said, "We do not argue with the critic who urges that the stars are not hot enough for this process. We tell him to go and find a hotter place." It is a rare moment of wit in a field not always known for it. And it is worth noting that he was writing this nearly a decade before Gamow worked out the quantum tunneling mechanism that explained how fusion could actually occur at stellar temperatures. Eddington knew the destination before anyone had mapped the road. There is a misconception worth addressing carefully here, because it appears frequently even in documentaries and popular science books. The misconception is that the sun is essentially a giant hydrogen bomb, that the fusion in its core is the same process as a thermonuclear weapon, just larger. This framing is misleading in a crucial way. A hydrogen bomb releases its energy in a fraction of a second in an uncontrolled chain reaction. The sun releases its energy over billions of years in a carefully self-regulated process. The rate of energy production per unit volume in the sun's core is actually quite modest, by engineering standards roughly comparable to the metabolic heat output of a compost heap per cubic meter of volume. The sun is not an explosion. It is the opposite of an explosion. It is one of the most stable and self-regulating energy sources in the universe. The reason it is so luminous is not because its energy production rate is high. It is because the sun is so enormously large that the modest energy production per unit volume multiplied across its entire core amounts to an output of approximately 3.8 times 10 to the power of 26 watts. That is a number so large that it resists intuitive comprehension, but it is produced slowly, steadily, and self-regulatedly by a process that will continue for another 5 billion years. This self-regulation is something Eddington grasped intuitively before the mechanism was understood. He recognized that whatever was powering the sun must be self-governing, because the sun had been remarkably constant in its output, for geological timescales far too stable for any process that was not automatically self-correcting. Fusion, as it turns out, is self-correcting in precisely the way required. If the core gets too hot, fusion accelerates, pressure increases, the core expands slightly, temperature drops, fusion slows. If the core cools slightly, pressure drops, gravity compresses, the core temperature rises, fusion accelerates. The star breathes, not dramatically, not visibly, but it breathes in cycles measured in thousands of years, maintaining its equilibrium through a feedback loop that is elegant in its simplicity. The T Tauri phase, the period just before a solar mass star fully settles onto the main sequence, is one of the most observationally rich stages in stellar formation, and one that was not understood for a long time. T Tauri stars are named after the prototype object, T Tauri itself, discovered in 1852 by the British astronomer John Russell Hind. Hind noticed a variable star embedded in a small reflection nebula in the constellation Taurus, surrounded by nebulous material that seemed to vary in brightness independently of the star itself. For decades, T Tauri was classified simply as an irregular variable, a star that changed brightness unpredictably for unknown reasons. It was not until the 1940s and 1950s that Alfred Joy at the Mount Wilson Observatory compiled a catalog of similar objects and recognized them as a distinct class young pre-main sequence stars, still in the process of contracting and clearing their surrounding material. Today, T Tauri stars are understood to be stars of roughly solar mass that have not yet ignited stable hydrogen fusion, are still accreting material from their circumstellar disks, and are magnetically extremely active. They flare, they vary, they launch intense stellar winds that begin to clear the disk and the surrounding nebula, and they exhibit a phenomenon called FU Orionis outbursts, sudden increases in accretion rate that cause the star to brighten dramatically over months and then fade over decades. The first FU Orionis outburst was observed in 1936, when the star FU Orionis in the constellation Orion increased in brightness by a factor of about 250 in less than a year. Astronomers at the time were baffled. The phenomenon was not understood until much later, when it was recognized as a sudden instability in the protostellar disk that floods the stellar surface with accreting material, temporarily overwhelming the star's surface temperature and making it appear orders of magnitude brighter than normal. The transition from T-Tauri star to main sequence star, the crossing of the zero-age main sequence, happens not in a moment, but in a process. For a solar mass star, it takes about 50 million years from the beginning of the protostellar collapse to the final establishment of stable hydrogen fusion. During that entire time, the star is contracting, adjusting, testing its own balance, responding to the feedback between gravity and thermal pressure. And then somewhere in that gradual process, the core temperature rises past 10 million. Kelvin quantum tunneling begins to operate efficiently enough that the proton-proton chain runs continuously, and the contraction effectively stops. The star has arrived, not with a fanfare, not with an announcement, simply with a new kind of silence, the silence of equilibrium, of a balance that can be maintained. Have you ever reached a moment in your own life where something that had been in motion for a very long time simply settled into place, not dramatically, not with a celebration, but with a quiet sense of rightness, of having arrived somewhere real? The star does something like this. After millions of years of collapse and adjustment and turbulence and variable accretion, it simply becomes stable. The fires in its core find their rhythm, and it begins finally to shine. What ignites in the core of a forming star is not just energy, it is a kind of identity. Before fusion, the object was in transition, neither cloud nor star, defined more by what it was becoming than by what it was. After fusion, it is something complete, something that will hold its form, maintain its balance, and pour light into the surrounding space for millions or billions of years, depending on its mass. And it is that relationship between mass and destiny, between how much hydrogen a star is born with, and how it chooses in the language of physics to spend it, that carries some of the most surprising and counterintuitive lessons in all of stellar science. Because a star does not simply burn, it balances. And the balance it achieves tells a story about time and energy and the strange economy of existence that is unlike anything else in the universe. There is a red dwarf star in the constellation Pisces that has been burning quietly and steadily since before our solar system existed. It will still be burning long after the sun has swelled into a red giant, consumed the inner planets, and faded into a cold white ember. Its name is unlikely to appear in any mythology. It has no dramatic legacy in the history of astronomy. It is simply called von Manen's star, though that is actually a white dwarf, and the red dwarf we mean is a different unnamed member of that ancient population that will outlive almost every other star in the galaxy. It will shine in its dim and patient way for an estimated 10 trillion years. That is roughly 700 times the current age of the universe. And yet, there are other stars we can see right now with the naked eye that will exhaust their entire fuel supply in a few million years before the continents of Earth have had time to drift into significantly new configurations. Same physics, same fusion, same fundamental process, but outcomes separated by a factor of millions. The difference between these stars is not mysterious. It is, in fact, one of the most instructive stories that stellar physics has to offer, a story about balance and what happens when that balance is struck at different scales. We ended the last chapter at the moment of ignition, the quiet, undramatic establishment of nuclear fusion in the core of a forming star, the arrival at what physicists call the zero-age main sequence. That moment is not an ending. It is the beginning of the longest and most stable phase in any star's life. And understanding what makes that stability possible and what determines how long it lasts requires looking carefully at the balance that every star must strike and maintain moment by moment for its entire productive life. Every star that has ever shone in the universe is engaged in a negotiation between two forces that are trying simultaneously to destroy it. Gravity is trying to collapse it inward toward a point. Thermal and radiation pressure, the outward push of hot gas, and the momentum of the photons generated by fusion is trying to blow it apart outward into space. A star is neither collapsing nor exploding, only because these two forces are at every moment in precise balance. The technical name for this balance is hydrostatic equilibrium, and it is the defining condition of a main sequence star. Remove the fusion and gravity, winds the star collapses. Add too much pressure and radiation, winds the star disperses. The star exists only in the narrow space between these two outcomes, held there by the same self-regulating feedback we explored in the previous section, operating continuously across a volume that in the case of the Sun contains 2 times 10 to the power of 30 kilograms of plasma. This equilibrium is not a static thing. It is a dynamic balance like a tightrope walker who maintains stillness through constant small adjustments, never truly motionless, always responding, always correcting. And the nature of the adjustments a star must make depends enormously on how much mass it has. Mass is in stellar physics almost everything. It determines the internal temperature, which determines the rate of fusion, which determines the luminosity, which determines the lifespan. Every major characteristic of a star flows ultimately from a single number, its mass at birth. The relationship between mass and luminosity in main sequence stars was one of the great discoveries of early 20th century astrophysics. It was established empirically by Arthur Eddington, the same Eddington who proposed hydrogen fusion as the stellar energy source through analysis of the masses and luminosities of binary star systems, where masses can be measured directly from orbital mechanics. Eddington published his mass-luminosity relation in 1924, and it showed something remarkable: luminosity scales not linearly with mass, but as approximately the 4th power of mass. A star twice as massive as the Sun is not twice as luminous, it is approximately 16 times as luminous. A star 10 times as massive as the Sun is not 10 times as luminous, it is approximately 10,000 times as luminous. This steep relationship has profound consequences for stellar lifetimes. Lifetime for a star is essentially a fuel-to-consumption ratio. A more massive star has more hydrogen fuel, but because of the mass-luminosity relation, it burns that fuel at a disproportionately higher rate. The net effect is that more massive stars have dramatically shorter lives. A star of 10 solar masses has roughly 10 times more hydrogen than the Sun, but burns it at roughly 10,000 times. The rate meaning its lifetime is approximately 10,000 divided by 10 or 1,000 times shorter than the Sun's. The Sun will live approximately 10 billion years on the main sequence. A star 10 times more massive will live only about 10 million years. A star of 50 solar masses may exhaust its core hydrogen in only a few million years. Meanwhile, a red dwarf with half the Sun's mass burns its hydrogen so slowly that it will remain on the main sequence for 100 billion years or more, 10 times longer than the current age of the universe. This is worth pausing on because it inverts a common intuition. We tend to assume that more resources mean a longer life. A larger star has more fuel, surely it burns longer. But the physics of hydrostatic equilibrium requires that a more massive star maintain a much higher core temperature and pressure to hold itself against its own stronger gravity. Higher temperature means faster fusion. Faster fusion means more luminosity. More luminosity means faster fuel consumption. The star is, in a sense, a victim of its own weight. The more massive it is, the harder it must work to hold itself together, and the faster it burns through everything it has. The most massive stars known to exist, objects like R136A1 in the Tarantula Nebula of the Large Magellanic Cloud, with a mass estimated at around 170 to 300 solar masses, are so luminous that they approach, and in some analyses may exceed what is called the Eddington luminosity limit. This is the theoretical maximum luminosity a star can achieve before radiation pressure alone would be sufficient to blow away its outer layers. Eddington derived this limit mathematically in the 1920s, and it represents a kind of ceiling, a point beyond which the outward push of radiation overwhelms the inward pull of gravity at the stellar surface. Stars near or above this limit are inherently unstable. They shed mass in powerful stellar winds, losing the equivalent of the Earth's mass every year in some extreme cases. They flicker. They vary. They occasionally eject entire shells of their outer layers in explosive events called luminous blue variable eruptions, of which the most famous historical example is Eta Carinae, a massive star system in our own galaxy that underwent a spectacular outburst in 1843, temporarily becoming the second brightest star in the night sky, visible in daylight from the southern hemisphere, before fading back below naked-eye visibility over subsequent years. Eta Carinae is approximately 7,500 light-years away. The outburst was so energetic that it briefly rivaled supernovae in luminosity, yet the star survived ejecting a bipolar nebula of gas and dust, called the Homunculus Nebula, that is still expanding today and can be observed in infrared images as two lobes of glowing material surrounding the star. Astronomers believe Eta Carinae is a strong candidate for the next naked-eye supernova visible from Earth, though the timing of this event, whether it will occur in 1,000 years or 1,000,000, remains unknown. When it does explode, it will be visible in daylight and will briefly outshine every other star in the night sky. The light from that explosion is at this moment traveling toward us, or perhaps it has already arrived and we have not yet lived to see it. The contrast between Eta Carinae and a low-mass red dwarf is one of the starkest in all of nature. Eta Carinae is so luminous that the radiation pressure at its surface is constantly fighting gravity to a near draw. A red dwarf of 1/10th solar mass is so dim, radiating perhaps 1/10,000th of the sun's luminosity, that convection currents stir the entire star from core to surface, mixing fresh hydrogen down into the fusion zone and gradually consuming nearly all of the star's available fuel over trillions of years. Red dwarfs do not have distinct cores and envelopes the way the sun does. They are fully convective, thoroughly mixed, which means they are more fuel efficient than larger stars, in a quite literal sense. They use almost everything they have. The sun, by contrast, will only fuse the hydrogen in its core, which constitutes about 10% of its total hydrogen. When that core hydrogen is exhausted, the sun will leave the main sequence even though 90% of its hydrogen remains unburned in its outer layers. A red dwarf would find this profligate. It burns almost everything slowly for an almost incomprehensibly long time. There is a classification system for stars called the Morgan-Keenan system that organizes main sequence stars into spectral classes based on their surface temperature, and by extension, their mass and color. The classes in order from hottest and most massive to coolest and least massive are O, B, A, F, G, K, and M. Generations of astronomy students have remembered this sequence with various mnemonics, the most printable of which is, "Oh, be a fine girl, kiss me." The sun is a G-type star, right in the middle of the sequence, comfortable and moderate in every way. O and B-type stars are the massive hot blue giants, the Eta Carinae class, brilliant and brief. M-type stars are the red dwarfs, the von Manens class, dim and ancient and extraordinarily long-lived. The sequence spans an enormous range of conditions. The hottest O-type stars have surface temperatures exceeding 50,000 Kelvin and masses up to 100 solar masses or more. The coolest M-type dwarfs have surface temperatures around 3,000 Kelvin and masses as low as 8/100ths of a solar mass, the minimum mass needed to sustain stable hydrogen fusion at all. Below that minimum, below about 8% of the sun's mass, something forms that is neither fully a star nor a planet. And we will return to that threshold in a later part of this journey. But within the stellar range, the mass-luminosity lifetime relationship creates a remarkable diversity of objects that all arise from the same fundamental physics of hydrostatic equilibrium, all governed by the same four forces of nature, all fusing the same hydrogen in their cores, yet producing outcomes as different as a mayfly and a tortoise are different in lifespan, or as different as a candle and a lightning bolt are different in intensity. Here is something that is rarely discussed outside technical literature, but that carries a kind of quiet wonder in it. The sun is currently about halfway through its main sequence life. It has been fusing hydrogen in its core for approximately 4.6 billion years, and it has approximately 5 billion years remaining before its core hydrogen is exhausted. During all of that time, all 9 to 10 billion years of stable main sequence burning, the sun will change only very gradually. It will grow slightly more luminous over geological time, as the helium building up in its core slightly alters the pressure balance and the fusion rate adjusts. It will not dramatically change its appearance, its size, or its fundamental character. This extraordinary stability, billions of years of near constancy, is itself a product of the hydrostatic equilibrium we have been discussing. The self-regulating feedback loop of fusion and gravity is so robust that it maintains the star in an almost unchanging state across timescales that dwarf the entire history of complex life on Earth. And this stability was essential for us. Life on Earth has required a stable, consistent energy source for nearly 4 billion years. Not too bright, not too dim, not varying wildly from century to century. The sun's position on the main sequence, its specific mass, which determined its luminosity, its temperature, its stability, was not tuned for us in any intentional sense. But it was necessary for us in a deep physical sense. A more massive star would have burned out before complex life had time to evolve. A much less massive star would have been dim enough, and its habitable zone narrow enough and tidally constrained enough that the conditions for complex life might have been significantly more difficult to sustain. The sun's place on the main sequence, its comfortable, moderate G-type stability, is part of why we exist to observe it. Have you ever thought about the fact that the specific mass of a cloud of gas that collapsed nearly 5 billion years ago is the reason that you are here thinking these thoughts in this moment? That the number of hydrogen atoms that happen to fall together in one particular region of an unremarkable molecular cloud on an outer arm of an average spiral galaxy set in motion a chain of physical consequences that would eventually produce, among other things, the capacity for wonder itself. The balance a star maintains that quiet, constant negotiation between collapse and dispersal, between gravity and light, is not merely a physical condition. It is, in a very real sense, the condition of possibility for everything that depends on starlight. Every photon that has ever warmed a planetary surface, driven a chemical reaction, energized a biological process, every one of those photons is a product of that balance. A leak in the dam. A small excess of fusion energy finding its way out from the core, traveling through hundreds of thousands of years of radiative transfer and convection before finally escaping as light. The star does not intend to illuminate. It simply cannot hold everything in. And in that slow, steady inability to contain its own fire, it makes worlds possible. What happens when that balance finally breaks, when the hydrogen in the core is exhausted and gravity begins to win again, is one of the most dramatic sequences in stellar evolution, and it sets the stage for everything that will follow in this story. But we are not quite there yet, because there is a class of objects that never achieved the balance in the first place. Objects that fell toward starhood gathered mass, warmed their cores, and then stopped just short of the threshold. Suspended between cloud and star, drifting in the dark, neither one thing nor the other. They are the universe's unfinished sentences, and their story deserves to be told. 4.5 billion years ago, In an unremarkable corner of an unremarkable spiral galaxy, there was nothing. No sun, no Earth, no solar system of any kind. Just a slowly drifting region of molecular cloud, cold, hydrogen, and helium, laced with traces of heavier elements threaded with dust, turning almost imperceptibly in the dark. And somewhere in that cloud, something happened. A disturbance, a ripple, a shockwave from a dying star somewhere nearby, pressing into the gas, tipping a dense knot of material past the threshold of stability. The cloud began to fall, and from that fall, from that one quiet collapse among countless others, happening simultaneously across the galaxy, came everything. The sun, the planets, the oceans, the first cell that divided in a warm, shallow pool, the first creature that looked up at the sky, the mind that is right now listening to this story about its own origin. The sun was not always a star, it was once a cloud, and the story of how that cloud became our sun is the most personal story that astronomy has to tell. We have been following the physics of star formation in its general form: molecular clouds, gravitational collapse, protostars, fusion, ignition, hydrostatic equilibrium. All of that was necessary groundwork. But now we turn to a specific case. The case we know most intimately because we live inside its consequences. We turn to the origin of our own solar system, and to the remarkable body of evidence written in meteorites and isotope ratios and orbital geometries that allows scientists to reconstruct what happened here 4.5 billion years ago, with a precision that continues to astonish even the researchers doing the work. The cloud that became the solar system is referred to in the scientific literature as the solar nebula, and it existed as a coherent, slowly collapsing structure for perhaps a few tens of millions of years before the collapse that ultimately produced the sun. Its composition was not random. It was the product of everything that had happened in the galaxy up to that point: supernova explosions, stellar winds, the slow accumulation of heavier elements through generations of stellar birth and death, stretching back billions of years before our sun existed. The solar nebula was, in chemical terms, a library of cosmic history, and the pages of that library are still accessible to us, preserved in some of the oldest objects in the solar system. Meteorites are in many respects the most scientifically valuable rocks on Earth, not because they are rare, thousands fall every year, but because some of them have been chemically unchanged since the formation of the solar system. The most primitive of these are called carbonaceous chondrites, and within them are tiny ancient grains called calcium aluminum-rich inclusions, or Ca. That are believed to be among the very first solid objects that condensed from the cooling solar nebula. Radiometric dating of these inclusions gives an age of 4,568,000,000 years, with an uncertainty of roughly 500,000 years in either direction. This date is, by scientific consensus, the age of the solar system. It is the moment when solid material first began to crystallize from the hot gas surrounding the young sun, the beginning of the planetary formation process that would eventually produce Earth. But within those same meteorites, there is evidence for something that took decades to fully appreciate. Certain isotopes variants of elements with different numbers of neutrons are found in ratios that can only be explained if freshly synthesized stellar material was injected into the solar nebula very shortly before or during its collapse. Aluminum-26, which decays radioactively into magnesium-26 with a half-life of approximately 730,000 years, is found in Ca, is at abundances that suggest it was alive, freshly produced when those grains formed. Aluminum-26 is produced primarily in the cores of massive stars and distributed through supernova explosions. Its presence in the early solar nebula in the quantities observed points strongly toward a nearby supernova occurring within perhaps 1 to 3 million years of the solar nebula's collapse. That supernova did not merely contaminate the solar nebula with fresh isotopes. It may have triggered the collapse itself, The same shockwave that deposited aluminum-26 into the cloud may have been the disturbance that pushed the dense core past the gene's threshold and set the gravitational collapse in motion. This evidence was not assembled quickly. The story of short-lived radioactive isotopes in meteorites spans more than half a century of careful laboratory work, beginning with the detection of excess magnesium-26 in CAIs by Typhoon Lee D.A. Papanastasiou and Gerald Wasserberg at Caltech published in 1976. Their paper, running to just a few pages in the journal Geophysical Research Letters, reported an anomaly in magnesium isotope ratios in a meteorite called Allende, a large carbonaceous chondrite that fell in Mexico in 1969, conveniently just months before the Apollo program would begin returning lunar samples, ensuring that geochemistry laboratories around the world were fully equipped and staffed to analyze extraterrestrial material. The Allende meteorite arrived in a sense at exactly the right moment in scientific history. Its fall was unplanned, its timing was extraordinary, and the isotopic anomalies it contained have driven decades of research into the conditions of the early solar system. The physical process by which the solar nebula transitioned from a collapsing cloud to a structured disk to a system of planets is called solar system formation or planetary accretion, and it proceeded in stages that are now reasonably well understood in their broad outlines, though many details remain actively debated. The solar nebula flattened into a rotating disk, the protoplanetary disk, as angular momentum conservation demanded. Within that disk, temperature varied dramatically with distance from the forming sun. Close to the center, within what is called the frost line, the distance at which water ice can exist, roughly 2.5 times the Earth-Sun distance, only refractory materials could survive: rocks, metals, silicates. Beyond the frost line, ice could persist, dramatically increasing the amount of solid material available for planet building. This temperature gradient is why the inner solar system contains small rocky planets, while the outer solar system contains large ice and gas worlds. The chemistry of formation was written into the geometry of temperature. The sun itself, during its protostella and early T-Tauri phase, passed through conditions that shaped the disk around it in ways that are still being unraveled. One of the most striking recent discoveries, made possible by the extraordinary resolution of the ALMA telescope array in Chile, is that protoplanetary disks around young stars show complex structured rings and gaps, concentric bright rings alternating with dark gaps, that suggest planet formation begins far earlier in the disk's history than previously thought. When astronomers first imaged the protoplanetary disk around H.L. Tauri, a young T Tauri star in the Taurus molecular cloud, only about 1 million years old, they were astonished to see a beautifully structured disk with at least 7 distinct rings and gaps. This star is younger than the gap-forming processes were thought to require. The implication is that planetary bodies, or at least the pressure structures that carve gaps in disks, can begin forming within the first 1 million years of a stellar system's history. The timeline for planetary formation has been pushed back dramatically by this single image published in 2014. Our own sun's protoplanetary disk would have looked something like this: concentric rings of gas and dust, the inner regions hot and rocky, the outer regions cold and icy, the whole structure rotating slowly around a central object that was still gathering mass from the infalling envelope above it, still launching bipolar jets along its rotation axis, still magnetically active and variable in ways that shape the chemistry of the surrounding disk. The young sun was not the stable, quiet star it is today. It was a T Tauri star, flaring variable, driving a powerful stellar wind outward through the disk, and eventually clearing the gas from the inner disk through a combination of photoevaporation and wind pressure. This disk clearing process, which occurred over the first few million years of the solar system's history, is what ended the accretion of gas onto the giant planet cores and set the final masses of Jupiter and Saturn. Jupiter deserves special mention in any account of the solar system's formation because its role was not passive. Jupiter's enormous gravity, it contains more than twice the mass of all the other planets combined, shaped the architecture of the entire solar system. Models of early solar system dynamics, particularly a framework called the Grand Tack hypothesis, developed by Kevin Walsh and colleagues and published in 2011, suggest that Jupiter may have migrated significantly inward during the early solar system, possibly reaching the current orbit of Mars before being pulled back outward as Saturn formed and became locked in a gravitational resonance with it. This inward then outward migration, the Grand Tack would have scattered and truncated the material available to build the inner terrestrial planets, explaining why Mars is so much smaller than Earth and Venus. It would also have implanted water-rich asteroids and primitive carbonaceous material into the inner solar system, seeding Earth with some of the water and organic compounds that would eventually make life possible. Jupiter was not merely a large planet orbiting at a safe distance. It was an active architect of the inner solar system's composition. Some scientists have even argued that without Jupiter's specific mass and orbital history, Earth might have been a very different kind of world. And then there is the water. The origin of Earth's water is a question that scientists have been working on for decades. And the answer that is emerging carefully with many uncertainties still in place points toward a solar system history far more dynamic and interconnected than the neat concentric rings diagram of planetary formation suggests. Earth formed in the dry inner solar system inside the frost line from rocky and metallic material. Early Earth should have been largely waterless. Yet, Earth has oceans. Enormous deep life-sustaining oceans. Where did the water come from? The leading hypothesis supported by isotopic measurements of water in asteroids and comets is that much of Earth's water was delivered by carbonaceous chondrite asteroids, primitive water-bearing rocks from the outer asteroid belt during a period of heavy bombardment in the early solar system's history. The hydrogen isotope ratio in Earth's oceans, the ratio of ordinary hydrogen to deuterium, most closely matches the isotopic signature of carbonaceous chondrite meteorites, suggesting that asteroids were a major source. The exact contribution of comets remains debated since comet water often has a different isotopic signature, but the broad picture that Earth's water arrived from elsewhere in the solar system, carried by objects that form beyond the frost line and were gravitationally scattered inward by the dynamics of the early system, is now the mainstream scientific view. There is something almost vertiginous about this if you let yourself sit with it. The water in your body, the water that comprises roughly 60% of your mass that flows through your cells, that carries the chemistry of life in solution, began as ice on a primitive asteroid in the outer solar system, billions of years ago. That ice formed in the cold outer regions of the solar nebula around grains of dust in temperatures barely above absolute zero. It survived the violent early solar system. It was scattered inward by Jupiter's gravity. It collided with the early Earth. It became oceans. It became rain. It became rivers. It became the medium in which eventually chemistry became biology. The water is ancient. It has been water in one form or another since before the Earth existed. You are carrying the solar nebula inside you. Have you ever held a glass of water and thought about where it came from? Not the tap, not the reservoir, not the water cycle, but the deepest origin. The answer begins in a cold, dark cloud of gas and dust, 4.5 billion years ago, in a quiet corner of the Milky Way that had no particular reason to be extraordinary, and became the most important place in the universe for us. The story of our sun is in the end not a story about a star. It is a story about inheritance, about a cloud that received material from dying stars, collapsed, sorted itself by temperature and chemistry, built a family of worlds, and eventually, after billions of years of quiet, stable burning, created the conditions for something unprecedented to emerge on a small, wet, rocky planet at just the right distance. The sun did not know it was doing any of this. It was simply following the physics. But the physics led here. And here, as it turns out, is a place where someone can look up at the sky and begin to understand the story. There is another chapter in this story that runs alongside the solar history. We have been tracing a chapter about the objects that almost became stars, but didn't quite make it. Objects that collapsed, warmed, and then stalled at the very edge of the threshold that separates starlight from darkness. They are more numerous than most people realize, and they drift invisible through the galaxy in enormous numbers. Some astronomers believe there may be more of them than there are true stars, and what they are and what they are not is a story about thresholds and about what it costs in the currency of mass to truly become a light in the universe. Somewhere in the darkness between the stars, drifting alone through interstellar space with no sun to orbit and no light to cast, there is an object the size of Jupiter, but perhaps 80 times more massive. It is not a planet. It is not a star. It has never been either, and it will never become either. It formed the way stars form from the gravitational collapse of a molecular cloud. It passed through a protostellar phase. It developed a rotating disk. It may even have launched bipolar jets into the surrounding nebula. It did almost everything a star does in its formation, and then it stopped. Just short of the threshold, just short of the temperature and pressure needed to sustain the nuclear fusion that would have made it a star. It has been cooling slowly and invisibly ever since. It will continue cooling for billions of years, radiating a faint warmth that no planet orbits and no civilization will ever use. It drifts in the dark, neither one thing nor the other, carrying within it the record of a formation process that went almost all the way, and then at the very last moment did not quite arrive. These objects are called brown dwarfs. And the story of what they are, how they were found, why they were so difficult to detect, and what they tell us about the thresholds that separate different kinds of cosmic objects. That story is one of the most fascinating chapters in modern astronomy, and one that most people have never heard told in full. We ended the previous section with the solar story, with the remarkable chain of events that took a molecular cloud, collapsed it, built a star and a family of planets, and eventually produced oceans and life and the capacity for wonder. But that story was one of success, a collapse that crossed every threshold and produced something complete. The story of brown dwarfs is a story about the threshold itself, about what happens when the physics almost works, about the universe's vast population of objects that began the journey towards starhood and traveled most of the way and then ran out of what they needed to finish. To understand where brown dwarfs sit in the landscape of cosmic objects, it helps to think about mass as a currency that buys different physical outcomes. At the low end of the mass scale, you have objects that are clearly planets incapable of fusing any element under any circumstances, warmed only by their formation, heat, and whatever radiation they receive from a host star. Above approximately 13 times the mass of Jupiter objects become capable of fusing deuterium, a heavy isotope of hydrogen, briefly during their formation before exhausting that fuel and cooling. This deuterium-burning phase is one of the defining characteristics used to separate brown dwarfs from giant planets. Though the boundary is actively debated, above approximately 65 to 80 times the mass of Jupiter, the exact number depends on composition and is still refined by ongoing research. Objects become capable of sustaining stable hydrogen fusion, and they cross the threshold into true stellar status, becoming the lowest mass red dwarf stars. Brown dwarfs occupy the space between these two thresholds, between roughly 13 and 80 Jupiter masses, capable of some fusion, but not the stable self-sustaining hydrogen fusion that defines a true star. They are, in the language of astrophysics, substellar objects. Below the stellar minimum, above the planetary maximum, a category unto themselves. The existence of brown dwarfs was predicted theoretically long before any were confirmed observationally. The Indian-American astrophysicist Shiv Kumar is generally credited with the first theoretical treatment of very low-mass objects published in 1963. in which he derived that objects below a certain mass threshold could not sustain stable hydrogen burning and would instead contract indefinitely, cooling over time. Kumar called these objects black dwarfs, a term that would later be reassigned to a different class of objects entirely, and his paper was largely ignored for more than a decade. In 1975, Jill Tarter, then a graduate student at the University of California, Berkeley, and later to become famous for her decades of leadership in the search for extraterrestrial intelligence, used the term brown dwarf in her doctoral dissertation, coining the name that would stick. Tarter chose brown as a descriptor because it suggested something intermediate between the red of the coolest true stars and the complete darkness of a non-radiating object, though she later noted that brown dwarfs, if you could somehow see them up close, would likely appear deep magenta or dark orange rather than brown. For the next 2 decades after Tarter's dissertation, brown dwarfs remained theoretical. No confirmed detection existed. This was not for lack of trying. The problem was observational brown dwarfs are faint, extraordinarily faint. A brown dwarf at the deuterium burning threshold radiates perhaps 1/10,000th of the sun's luminosity in visible light. Most of its emission is in the infrared at wavelengths, where the atmosphere absorbs and where detectors were, until the 1990s, far less sensitive than they are today. Finding a brown dwarf was, as one astronomer memorably put it, like looking for a dark red ember in a dark room, except the room is the galaxy and the ember is 100 light-years away. The first confirmed brown dwarf was announced in 1995, the same year remarkably as the first confirmed detection of a planet orbiting a sun-like star, the year that the HL Tauri disk image would have seemed impossible, and just a year after the Hubble Space Telescope received its corrective optics and began returning sharp images. 1995 was, in retrospect, a watershed year for planetary and substellar astronomy. The brown dwarf was designated Gliese 229b, and it was found by Tadashi Nakajima and colleagues using the Palomar Observatory's 60-inch telescope, combined with a coronagraph, a device that blocks the light of a bright star to reveal faint companions nearby. Gliese 229b is a companion to the red dwarf star, Gliese 229, located approximately 19 light-years from Earth in the constellation Lepus. Its spectrum, when obtained, was unlike anything previously seen in astronomy. It showed absorption bands from methane, a molecule that had never been detected in the spectrum of any stellar object before, because methane is destroyed at the temperatures of even the coolest true stars. The presence of methane in Gliese 229 B's spectrum was immediate confirmation that this was something genuinely new, an object cool enough that methane could survive in its atmosphere, a brown dwarf unambiguously identified for the first time 32 years after Kumar's theoretical prediction. Almost simultaneously, a separate team led by Ben Oppenheimer at Caltech independently confirmed the nature of Gliese 229b using spectroscopy, and the 2 papers were published together in the journal Science in November 1995. The discovery was celebrated as the opening of a new chapter in the study of low-mass objects. It also raised an immediate question that researchers are still working to fully answer: how many brown dwarfs are there? The answer, as it has emerged over the subsequent 3 decades, is an enormous number. Brown dwarfs appear to be comparably abundant to true stars in the Milky Way, meaning there may be one brown dwarf for every true star in the galaxy, implying hundreds of billions of these dim, invisible objects drifting through the interstellar space around us. Many are companions to stars like Gliese 229b, but many others are isolated, free-floating brown dwarfs that formed alone from small molecular cloud cores, or that formed in stellar systems and were subsequently ejected by gravitational interactions. These free-floating objects, sometimes called rogue brown dwarfs, or isolated planetary mass objects, depending on their mass, drift through interstellar space unattached to any star, detectable only through infrared surveys that specifically search for faint, cool red objects against the stellar background. The classification of brown dwarfs has itself become a rich subfield of astronomy. Following the Morgan-Keenan spectral classification system used for stars, the OBAFGKM sequence, astronomers needed to add new spectral classes to accommodate the brown dwarfs, whose temperatures fall below those of the coolest M-type red dwarf stars. In 1999, the spectral types L and T were formally introduced. L dwarfs with surface temperatures between approximately 2,000 and 1,400 Kelvin represent the warmest brown dwarfs and the coolest objects that can still be called stars if they are above the hydrogen burning limit, or brown dwarfs if they are below it. T dwarfs with temperatures between approximately 1,400 and 700 Kelvin are the methane-bearing brown dwarfs like Gliese 229. Be cool enough for methane to form with distinctive near-infrared spectral signatures. In 2011, a further class was introduced, the Y dwarfs, for objects cooler than 700 Kelvin, some of which have surface temperatures approaching room temperature. The first Y dwarfs were discovered by the Wide Field Infrared Survey Explorer, or WISE satellite. The coolest confirmed Y dwarf found to date has a surface temperature estimated at approximately 200 to 300 Kelvin cooler than the surface of Venus, and within the range of temperatures comfortable for human habitation. These are objects that, if you somehow found yourself standing on their surface, would feel approximately as warm as a hot summer day. They are, in a very literal sense, barely warm at all. There is a common and understandable misconception that brown dwarfs are simply failed stars objects that tried to become stars and failed carrying some sense of cosmic inadequacy in their cool, dim interiors. This framing is worth gently setting aside because it imposes a hierarchy on nature that the physics does not actually support. A brown dwarf did not fail to be a star, any more than a river fails to be an ocean. It is a different kind of thing, with its own characteristics, its own internal physics, its own evolutionary trajectory. Brown dwarfs do undergo fusion, just not the sustained hydrogen fusion of true stars. The more massive brown dwarfs in the deuterium-burning range fuse deuterium in their cores for tens to hundreds of millions of years, after formation generating genuine nuclear energy and genuine stellar-type luminosity during that period. Some brown dwarfs above approximately 60 Jupiter masses are also capable of fusing lithium, a reaction that occurs at slightly lower temperatures than hydrogen fusion, and the presence or absence of lithium absorption in a brown dwarf spectrum, known as the lithium test, is actually used as a diagnostic tool to distinguish brown dwarfs from very low-mass red dwarf stars. The lithium test was proposed by Rafael Rebolo, Eduardo Martin, and Maria Rosa Zapatero Osorio in 1992, and has since become one of the standard methods for brown dwarf identification. What happens inside a brown dwarf over long timescales is itself a story worth telling carefully, because it differs fundamentally from what happens inside a true star. A true star, as we explored in the previous section, maintains hydrostatic equilibrium through the continuous generation of fusion energy that balances gravity. When its fuel is exhausted, it undergoes dramatic structural changes, the death sequences that produce red giants, planetary nebulae, white dwarfs, neutron stars, or black holes depending on mass. A brown dwarf has no such dramatic endpoint. It simply cools continuously over billions and then trillions of years. Gravity compresses it into a degenerate state, a state where the pressure resisting further compression is provided not by thermal motion, but by quantum mechanical electron degeneracy pressure, the same physics that holds up white dwarf stars. But unlike a white dwarf, which is the remnant of a star that has gone through its entire nuclear life cycle, a brown dwarf reaches the degenerate state without ever having been a true star at all. It begins its life as a warm infrared bright object and gradually becomes cooler, dimmer, and more infrared faint over cosmic time scales eventually becoming, after many hundreds of billions of years, something so cool and dark that detection would require instruments beyond anything we currently possess. The timescale here carries its own kind of weight. The universe is currently 13.8 billion years old. The coolest brown dwarfs cool to room temperature in perhaps 10 to 20 billion years. There are Y dwarf brown dwarfs out there that have already been cooling for the entire age of the universe, objects that formed shortly after the first stars lit up the cosmic dark ages and have been cooling ever since, now sitting at temperatures that would feel familiar to anyone who has walked outdoors on a warm afternoon. They are, in that sense, the universe's memory objects that have been present for virtually all of cosmic time, watching everything from the first galaxies to the present day, saying nothing, emitting nothing but a faint warmth that almost no instrument has been sensitive enough to detect. Have you ever thought about what it would mean to be present for almost all of cosmic time, to have existed since nearly the beginning, to have witnessed every major chapter of the universe's story, and yet to be so quiet, so dim, so utterly invisible that no one even knew you were there until the very recent past? Brown dwarfs carry that quality. They are ancient, abundant, and until just 30 years ago, completely unknown. The discovery of brown dwarfs also changed how astronomers think about planetary systems. The same process that forms brown dwarfs' gravitational instability in a collapsing cloud can also operate inside protoplanetary disks, potentially producing very massive planets or brown dwarf companions through a different pathway than the core accretion process that built the rocky and giant planets of our own solar system. The boundary between a very massive planet formed by disk instability and a low-mass brown dwarf formed by cloud fragmentation is genuinely blurry, and the question of which formation pathway produced a given substellar companion in any specific system is often not definitively answerable. Nature, at the edge of its categories, tends not to respect the boundaries that human classification systems draw. There is a deeper lesson in the brown dwarf story that reaches beyond astronomy. Science spent more than 30 years looking for objects that theory required to exist, finding nothing and continuing to refine the theory and improve the instruments rather than abandoning the prediction. When the detection finally came in 1995 from a coronagraph on a 60-inch telescope that had been operating for decades, it validated not just the theoretical prediction, but the entire methodology of persistence in the face of null results. Gliese 229. B confirmed that patience in science is not passive. It is a form of rigor. The absence of a detection for 3 decades did not mean brown dwarfs did not exist. It meant the instruments were not yet good enough. And the researchers who kept looking, who kept building better detectors and designing better surveys and thinking more carefully about where to look, were right to keep looking. The universe between the stars is far more populated than it appears from Earth on a clear night. Between every pair of visible stars on average, there may be a brown dwarf drifting invisibly through the dark, a warm remnant of a formation process that went almost all the way carrying the same hydrogen and helium that built the first stars, never igniting into light, never warming a planet, but present nonetheless. Part of the galaxy's mass budget, part of the cosmic inventory, a thing that exists on its own terms in its own way, quietly occupying a category the universe did not bother to explain to us until we asked the right questions. We have traveled a long way in this journey, from the cosmic dark ages before the first star ignited, through molecular clouds and collapsing cores and protostellar disks through the first nuclear heartbeat, and the long, stable burning of the main sequence through the solar system's own origin story, and now through the quiet world of the objects that almost made it and found their own kind of existence in the space between categories. What remains is the final, most personal chapter of this entire story, the one that brings everything back to here, to now, to the matter that makes up the air in this room and the cells in your body, and the slow electrical signals traveling through your mind as you listen. The chapter that asks not how stars form, but what their formation means for us, for the atoms we are made of, for the planet we live on, for the extraordinary accident of chemistry and time that produced something capable of looking up and asking where it all began. There is iron in your blood right now, not a metaphor, not a poetic approximation. Actual iron atoms sitting inside hemoglobin molecules in your red blood cells, binding oxygen and carrying it through your body with every heartbeat. And those iron atoms, every single one of them, were forged in the core of a dying star. Not our sun. Our sun is not massive enough to fuse iron. The iron in your blood was made in a star that was at least 8 times more massive than the sun, that lived for perhaps 10 million years, that built heavier and heavier elements in nested shells around its core, hydrogen to helium, helium to carbon, carbon to oxygen, oxygen to neon, neon to silicon, silicon to iron. And then when iron accumulated in its core and the fusion reactions could no longer generate energy to hold the star against gravity, it collapsed in less than a second. And in the catastrophic rebound of that collapse, it exploded as a supernova, scattering everything it had built, all those elements, all that chemistry into the surrounding space, where it drifted for millions of years, where it eventually became part of a molecular cloud, where that cloud collapsed, where the solar nebula formed, where the Earth accreted, where the oceans gathered, where chemistry became biology, where eventually a red blood cell formed inside you, carrying an iron atom that has been traveling for billions of years to arrive right now in this moment, doing the work of keeping you alive while you listen to a story about where it came from. This is not mythology. This is not metaphor. This is chemistry and physics and the 4 billion-year chain of cause and effect that connects a supernova explosion to the breath you are taking right now. And if that does not strike you as one of the most extraordinary facts in the history of human knowledge, then perhaps we have not been telling it with the weight it deserves. We have traveled far in this journey, from the cosmic dark ages when the universe was dark and cold and held its first stars only as potential, through the molecular clouds, those vast cold nurseries of gas and dust, where gravity first began its patient work of assembly, through the protostellar phase when a collapsing core built a rotating disk and launched jets and warmed toward the threshold of fusion, through the ignition of nuclear fire, that quiet self-regulating moment when hydrogen first began to fuse and a protostar became a star, through the long, stable burning of the main sequence where hydrostatic equilibrium held everything in balance across billions of years, through the intimate story of our own solar system, built from a cloud that inherited its chemistry, from stars that lived and died before the Earth existed, and through the strange, quiet world of brown dwarfs, the universe's unfinished sentences drifting in the dark between the stars. Now, we arrive at the final question. Not how stars are born, but what their births mean, what is left behind, what we are made of, and why any of it matters. The story of stellar nucleosynthesis, the building of elements inside stars, is one of the great intellectual achievements of 20th century science, and it arrived through a paper so comprehensive, so foundational, that it is still cited today nearly 7 decades after its publication. In 1957, 4 scientists, Margaret Burbidge, Geoffrey Burbidge, William Fowler, and Fred Hoyle, published a paper in Reviews of Modern Physics with the straightforward title, Synthesis of the Elements in Stars. It ran to over 100 pages. It laid out for the first time in unified form the theoretical framework by which every element heavier than hydrogen and helium could be produced through nuclear reactions inside stars. The paper is almost universally known by its author's initials B2FH. It is to nuclear astrophysics what Darwin's On the Origin of Species is, to biology a single document that reorganized an entire field around a new and more powerful explanatory framework. William Fowler received the Nobel Prize in Physics in 1983 for his contributions to this work. Margaret Burbidge, widely considered one of the paper's most essential contributors, did not receive the prize, an omission that has been discussed extensively in the history of science as one of the Nobel Committee's more conspicuous oversights. What B2FH established in careful and mathematically rigorous detail is that the universe began with only hydrogen, helium, and trace amounts of lithium, the products of Big Bang nucleosynthesis in the first 3 minutes of cosmic history. Every other element on the periodic table was made later inside stars. Carbon, the backbone of all organic chemistry. The element that makes life, as we know it, chemically possible, was built in the cores of medium-mass stars through a reaction called the triple alpha process, in which 3 helium nuclei fuse to form a single carbon-12 nucleus. This process works only because of an extraordinary coincidence, or what Fred Hoyle famously argued could not be a coincidence involving the energy levels of the carbon-12 nucleus. For the triple alpha process to proceed at a rate sufficient to produce the carbon abundance we observe in the universe, carbon-12 must have a specific excited energy state at precisely the right energy. Hoyle predicted this energy state in 1953, before it had been measured based purely on the argument that carbon exists in the universe in large quantities and therefore the triple alpha process must work efficiently, which required this specific nuclear resonance. When William Fowler's team at Caltech measured the carbon-12 energy levels and found the predicted resonance, it was one of the most striking examples in scientific history of a prediction made from astrophysical observations being confirmed by nuclear physics experiments. Hoyle had essentially reverse-engineered the nucleus of carbon from the existence of carbon-based life. He had used biology to predict nuclear physics, oxygen, the element you are breathing right now, the most abundant element in Earth's crust. The third most abundant element in the universe by mass is produced primarily through a further reaction, in which a carbon-12 nucleus captures a helium nucleus to form oxygen-16. The competition between carbon production and oxygen production in stellar cores, a competition governed by nuclear reaction rates that were measured painstakingly in laboratories over decades, determines the carbon-to-oxygen ratio in the universe, which in turn determines fundamental aspects of the chemistry of life. If those reaction rates were slightly different, if the nuclear physics were even marginally altered, the ratio of carbon to oxygen in the universe would shift, and the organic chemistry that underlies biology would be substantially different or possibly not viable at all. These observations have been used by some physicists and philosophers to argue for the fine-tuning of physical constants, the idea that the universe's parameters appear surprisingly well-suited for the existence of complex chemistry. Others argue that this is simply the anthropic principle at work in a universe where carbon-based life exists. Observers will necessarily find themselves in a universe whose physics permits carbon. The debate remains lively and genuinely unresolved, which is part of what makes it interesting. The heavier elements iron, nickel, and everything lighter than iron are built progressively in the cores of massive stars, through successive fusion stages, each one extracting less energy from the fuel than the last, each one proceeding faster than the previous stage as the core temperature rises to compensate. A massive star spends millions of years fusing hydrogen. It spends hundreds of thousands of years fusing helium. Carbon fusion takes perhaps 1,000 years. Neon fusion weeks. Oxygen fusion months. Silicon fusion, the last stage before iron, takes approximately 1 day. And then iron accumulates in the core. Iron is the endpoint of exothermic nuclear fusion, the element beyond which fusing nuclei consumes energy rather than releasing it. When the iron core reaches approximately 1.4 solar masses, a limit related to the Chandrasekhar limit for white dwarf stability, named for the Indian-American physicist Subrahmanyan Chandrasekhar, who derived it in 1930 at the age of 19 during a steamship journey from India to England. It collapses catastrophically in a fraction of a second. The core implodes. The outer layers fall inward and then rebound in a shock wave of extraordinary violence. The star explodes as a core collapse supernova. In the seconds of a supernova explosion, nuclear reactions that could never occur in the relatively sedate interiors of stable stars, take place at frantic rates. The elements heavier than iron copper, zinc silver gold, platinum uranium, are produced primarily in two processes that occur during and after the supernova. The rapid neutron capture process, or R process, occurs in environments of extreme neutron density where atomic nuclei capture neutrons faster than they can undergo. Radioactive decay, building up very heavy neutron-rich nuclei that then decay towards stability-producing elements that cannot be made any other way. For decades, the astrophysical site of the R process was uncertain supernovae were considered the primary candidate, but the conditions seemed difficult to achieve in supernova environments. In August 2017, the answer arrived unexpectedly and dramatically. Gravitational wave detectors, LIGO and Virgo, detected the merger of two neutron stars, the first such event ever observed approximately 130 million light-years away. Follow-up electromagnetic observations detected a kilonova, an explosion of extraordinary luminosity produced by the collision, glowing bright blue and then deep red as freshly synthesized heavy elements powered the light. Spectroscopic analysis confirmed the presence of strontium, and by inference large quantities of heavier R process elements, including gold. The neutron-star merger had synthesized in a few seconds an amount of gold estimated at several times the mass of the Earth. The gold in your jewelry, if you are wearing any, was made in the collision of two neutron stars somewhere in the universe in the final milliseconds of a cosmic catastrophe that released more energy than the sun will produce in its entire 10 billion year lifetime. Think about that the next time you look at a gold ring. It is not just a symbol of something precious. It is a relic of a violence so extreme that it warped space-time itself, detectable 100 million light-years away, by instruments sensitive enough to measure a displacement smaller than 1,000th the diameter of a proton. And it ended up through 4.5 billion years of geological and biological history on a human finger on a planet that exists because a star was born from a cloud. There is a question worth asking, one that sits at the intersection of science and philosophy, and that I think is worth asking not rhetorically but genuinely. Does knowing that we are made of stardust change anything? Does understanding the billion-year chain of nuclear reactions and gravitational collapses and supernova explosions that produce the atoms of our bodies make the experience of being alive feel different? Different people answer this differently. Some find it diminishing. The reduction of human experience to physics seems to some to drain the room of meaning. But many scientists and many people who have truly absorbed the facts we have been discussing tonight find the opposite. Knowing where the iron in your blood came from does not make your blood less miraculous. It makes the miracle larger. It extends the story backward by billions of years. It connects your heartbeat to a supernova explosion, your breath to the triple alpha process in a stellar core, your body to the specific molecular cloud that collapsed 4.5 billion years ago in an unremarkable corner of the Milky Way. You are not separate from the universe looking at it from the outside. You are the universe organized into a temporary and extraordinarily unlikely configuration that is capable of looking at itself and wondering where it came from. Carl Sagan wrote in Cosmos that we are a way for the universe to know itself. He was not speaking metaphorically in the loose sense. He was pointing at something physically true. The atoms that make up a human brain capable of comprehending cosmology are the same atoms that were fused in stellar cores and scattered in supernovae and assembled through 4.5 billion years of planetary and biological evolution. The universe's self-knowledge, if we want to use that language, is genuinely made of stardust. It is not just a poetic statement. It is a description of what is happening right now in every human mind that has ever looked up at the night sky and asked what it was looking at. Have you ever looked at your own hand really, looked not glanced, and tried to feel the fact that the matter you are looking at is older than the Earth, older than the sun, assembled from clouds that drifted through the galaxy for billions of years before any living thing existed? It is one of those thoughts that can either slide off the surface of the mind without leaving a mark, or sink all the way in and change something quietly and permanently. I hope tonight it sinks in a little. The history of our understanding of stellar birth is itself a story worth honoring in these final moments, because the knowledge we have been sharing tonight did not arrive in a single moment of revelation. It was assembled painstakingly over more than 3 centuries by an unbroken chain of human curiosity. Newton gave us gravity in 1687. Helmholtz and Kelvin worked out gravitational contraction in the 1850s and 1860s. Eddington proposed hydrogen fusion in 1920. Gamow provided the quantum tunneling mechanism in 1928. Beatty worked out the proton-proton chain in 1939. Burbage Fowler and Hoyle published B2FH in 1957. Jill Tarter coined the term brown dwarf in 1975. The first brown dwarf was confirmed in 1995. The first protoplanetary disk rings were imaged by ALMA in 2014. The first neutron-star merger was observed in 2017. The James Webb Space Telescope began revealing protostellar cores in unprecedented infrared detail in 2022. Each of these steps was taken by human beings working with curiosity and patience, and instruments built from the same stardust as everything else, looking outward and inward, and finding that the two directions eventually lead to the same place. We began this journey in darkness, in the cosmic dark ages before the first star existed, when the universe was sealed in a fog of neutral hydrogen and no light traveled freely through space. We watched gravity pull the first clouds together. We followed a protostar through its formation, its disk, its jets, its slow warming toward the nuclear threshold. We lit the first fusion fire and watched a star settle into its long, stable life. We traced our own sun's origin from a cloud contaminated by a nearby supernova, built a solar system around it, delivered water from beyond the frost line to a small rocky planet. We visited the objects that almost became stars and found their own kind of existence in the in-between. And now, we have arrived at the end of the journey, which turns out to be the beginning of another one, the story of what those stars built and what that building eventually produced. The stars are not done. Right now, in the Orion Nebula, in the Carina Nebula, in the Eagle, nebula in 1,000 molecular clouds scattered across the Milky Way, new stars are forming, new protostellar cores are warming, new protoplanetary disks are flattening and developing rings. New planetary systems are being assembled from the materials that previous stellar generations forged and scattered. The process that began in the cosmic dark ages 13 billion years ago is ongoing tonight. The universe is still making stars, still building elements, still scattering the chemistry of possibility into the dark. And somewhere in all of that, in some cloud, in some galaxy that we may or may not ever be able to observe, a collapse is happening right now that will produce in a few billion years a star with a planet in the right place, with the right chemistry, at the right temperature for something to begin, for life to make its improbable, stubborn, extraordinary appearance in another corner of the cosmos. We cannot know if that is happening. We cannot see it, but the physics says it is possible. The chemistry says it is possible. And the fact that it happened here once at least that we know of says it is not entirely out of reach. That is the story of where stars begin. Not just in the physics of collapse and fusion and equilibrium, but in the long, patient, indifferent, and somehow magnificent tendency of the universe to build things. To take simple materials and complex forces and let them work over unimaginable timescales until something extraordinary emerges. A star, a planet, an ocean, a cell, a mind, a quiet night, and a voice telling a story, and someone listening in the dark. Thank you genuinely from the quiet heart of this channel for spending this time with us, for following this story from the first darkness all the way to here, for being curious enough to ask where the light comes from, and for being patient enough to listen to the answer unfold across 9 chapters of physics and history and wonder. If this journey gave you something of fact that surprised you, A thought that will stay with you a moment where the universe felt larger and more intimate at the same time, then it has done exactly what it was meant to do. Science told softly in the dark to someone who is willing to listen. The next story is already waiting. Another corner of the universe, another chain of cause and effect stretching across billions of years. Another set of questions that science has been quietly, patiently working on, questions whose answers will make the familiar feel strange and the strange feel somehow like home. Rest now. Let what you have heard settle into the places where ideas go, when you are not actively thinking about them. And when the next quiet night finds you, it will find you. Sleep well. Dream gently. Good night.